Thanks for the opportunity, Derek. It's a blast to be with you guys, and I'm really amazed at what you guys do. So I just quickly want to tell you what Swim is, because you probably don't know. SwimOS is an Apache licensed runtime platform that makes it really easy to build stateful, distributed, data-driven applications. So think of us as the application layer that can sit on top of the amazing plumbing that NATS provides. So, there are lots and lots of ways to get data from place to place, Kafka, Pulsar, and God knows what else. NATS, in my mind, is perfect for us. And I'm going to tell you exactly why. And it really comes down to the fact that NATS roots on subjects, which is what Derek said, right at the beginning of the day. And subjects in the Swim context are actors. Well, at least they get to actors very fast. So I'm going to tell you all about Swim and why NATS is perfect for us. But I want to give you an idea of scale. I have some examples to give you a bit later. When I talk about massive scale, how about a gigabyte per second of streaming data, a few nanoseconds per event, which is the rate at which we're consuming and constructing models on the fly today. So we have to be able to go fast. NATS is fabulous at that. And Swim is the application layer. Cool beans. So another way you can think about us is that Swim is an application or stream processor for a system which is a pub/sub system. And so data could come from anywhere. It could come from a database, but most frequently in our world, it comes streaming at us. The fundamental paradigm, the shift that I'm seeing happen is that the world is moving away from store then analyze to a model of analyze and act on the fly and then store if you feel like it. And I want to really emphasize this really important thing, that even though storage is moving to flash and everything else, most disks are still, 5-6 orders of magnitude slower than CPU memory. So storage is slow and a waste of time in general. What we're interested in is producing real-time insights that people can act on in real time. Okay, so I'd like you to think of Swim as being like LinkedIn for things. God, this is a very simplistic way of describing Swim to a bunch of real experts like you lot. But I want to seize on mentions that I've heard today about the actor model. So SwimOS basically subscribes to an event stream. By the way, in the case of NATS, we get this fabulous subject-based routing, which can go directly to actors, which we call web agents, okay? And these web agents are stateful concurrent actors, each of which represents typically a real thing in the world. Okay, so it's a data. Most frequently, it's a data source, not just a subject. And so each one of these web agents cleans up its own data. It actively consumes data from some real world source. It maybe labels it and analyzes that data itself. Okay, so it's a way of directly creating objects which are concurrent, each of which represents a real world thing. And so at all times, these web agents represent a mirror for the real world. But these web agents build a graph in memory in real time based on real world relationships that they find in the data, or they're instructed to find the data. So for example, containment. All these sensors are belong to the same thing. And I'll give you an example of that in a moment. Proximity, all these intersections are near each other, okay? Or this truck with bad braking behavior is near this inspector, okay? And there are other programmatic relationships which we can discover, like correlation and so on, which is very useful for finding bugs in things. And so Swim builds and continually modifies this graph kind of at the leaves of a tree, linking these web agents to each other. Now, why do we call them web agents? Well, they are, instead of having object IDs, they have URIs. That's how you find them. And they're concurrent processes and they're stateful. And a link is like a sub. Okay, link A to link B. If A links to B, then A gets to see the in-memory real-time state of B, and vice versa. Now we can attach semantics to these links, including joins and maps and various other things. But for now, just assume the simplest version of that link, which is it's a real-time view of the state of another agent of relevant state, okay? And then operators for analysis, learning, prediction, and so on can be attached to these web agents and they compute as data flows over them, okay? So we have a graph which is continually building and manufacturing itself, changing. And as data flows over each vertex in the graph, analysis, learning, whatever happens, and the results just stream up the tree, okay? So a graph for web agents is like an intelligent stream processing pipeline, and what pops out the far side is the answers. Where do they get delivered to? Oh, they get delivered to directly into real-time browser implementations of Swim. So we have a real-time abstraction for building real-time UIs. Okay, so let's break this down and go slowly. A web agent is kind of a digital twin of a thing. It's a stateful concurrent object which is built dynamically from the data for the thing. So we build a program, and I'm going to use traffic as an example here. This program sees data. Data belongs to some sensor. Cool. So I have a sensor which is responsible for parsing this particular piece of real world data. No. Create a new web agent for that and hand it its own raw data, and it will then process it and statefully evolve. So as data arrives, we create these new actors. Each actor then is responsible for parsing, cleaning its own data, and representing statefully in memory, somewhere in this graph, the state of that real world thing. Okay, so it consumes the raw events. By the way, these actors can go and get stuff because they're concurrent. I'm describing a push model of it, but there is a pull model too. Okay, so each of these things can statefully analyze data as it flows from the source. And one of the most important things that Swim has done is produce stateful streaming models of a ton of analytical functions, many of which you can find in Flink or Spark or wherever. But instead of assuming that we have batches of data, we simply work on the current state of things. So what Swim does is turn raw data into state, and then there is a distributed computation on the part of these actors to arrive at whatever you want to compute. Okay, and once again, web agent means the object ID is just a URI. So what we're doing is we're giving these little, and these really are microservices. Each one of these things gets a streaming API. So we're moving the world beyond JSON and REST towards something which is a streaming API. You sub to a streaming API, And from then on, you will get updates in real time. Okay, so let's kick the rest habit and move on in life. So each one of these web agents can do really cool things. It can analyze data to determine its state. So it just gets, say, an average or whatever it happened to be. It can produce alerts and analytics. It can do all the usual stuff, analytical functions. They can perform powerful queries, relational queries, graph type queries, and SQL type queries. And they can learn and predict. And I'm going to go through an example of that in a little bit more detail shortly. So raw data shows up, and SwimOS creates web agents. Web agents are responsible for taking the raw data in whatever form it shows up and turning it into relevant state for the program. Now, often raw data is very noisy and needs cleaning. It depends on what lives between us and the source. Now, what you see here is an example which I'm going to use throughout, which is traffic lights. Okay, cool. I have raw data arriving from every loop, every car crossing every loop, every button push, every traffic light itself, and a virtual object, which is called an intersection. And the intersection owns each one of the 80 or so sensors that belong to it, courtesy of them sharing a common latitude and longitude. Okay, and that's just part of their configuration. And we can just pick that out of the data. Okay, and so we'll say, oh, here is a new data item from a new sensor. It belongs to some new logical intersection. Go and create the logical intersection. But there's another intimate relationship here between the intersections in a region. So a very simple statement is, hey, intersection, link to each one of your neighbors. Okay, every other intersection within 1,000 yards. And that gives that intersection a real-time view of the state of all of its neighbors. Okay, and what are we going to do with that? Well, we're going to instruct this thing to learn and predict. Now, this notion of learning and predicting is very interesting because in the swim context, these are self-trained. And so a model I'd like to stick in your head is that these digital twins learn a little bit like you and I do. They form theories and then they try them out with real data, and then they observe what the real world did, and then they feed back and form new theories, and on we go. So these are self-trained. You could always augment them with training data, I guess. Self-trained, small, relatively small DNNs, in which case an application is composed of lots and lots of DNNs which are learning in parallel. Way cool thing here. These are self-constructing models. So when a digital twin of an intersection shows up, it creates an empty DNN whose links are all random numbers, and which is dimensioned based on the number of sensors that it has and the number of sensors that it can see in its local environment. Okay, so I have a digital twin of an intersection. It's told to go off and learn and predict. And whenever it wants to, that is either based on the clock or some other constraint, it forms an input vector from the values of its own sensors and those of its neighbors, and throws them into a DNN. Sorry, somehow my DNN has disappeared. And then simply waits for the output. Okay, now the output the first time around is just going to be a guess. But then we get to see what happens in the real world and do a feedback loop and do go around the loop again. Okay, so that's back propagation. And there are lots and lots of local optimizations which are available. By the way, all this is open source, go play. So what we can do is just sit and go around this loop a lot, and these things self-track. So we can check whether the error rate or the error on predictions is converging or diverging. If it's diverging, okay, we're in a bad place. But if it's converging, good, pick an operation point, and once you're trained, you go. Now, what have I described to you? I've described to you a system which, given data, will build a model of the real world. The model is a graph. And then the elements, the vertices in this graph, will form theories, learn, and predict. Notice no data scientists, no storing data in the cloud, training models and pushing them to the edge. That's all bunk anyway. We all know that. Okay. So how does it all work? Notice I've described only application layer stuff. Okay, and that's all in this mauve, I guess, circle at the top. Swim is deployed as a set of instances which will run in some hybrid configuration. We don't really care where. So Kubernetes is perfect for us. So Kubernetes below us to figure out how many instances, where the instances are, and so on. And then the instances interconnect using WebSockets. So I love what's going on with WebSockets in the NATS world. We're huge fans. WebSockets are used really to as envelopes for the gazillion communications between the individual web agents in the model at the layer above, okay? And the protocol we use to update state on the part of the model elements, so each one of these little objects is called warp, sorry about the clash. It's just an update in the state for a particular web agent, which is transmitted over warp. Again, all open source. So Swim at runtime is composed of some number of instances, and these instances receive data. The awesome thing about NATS is NATS, with its subject-oriented routing, can really help us here because it can it distributes the whole task. Other than that, Swim contains, I guess, hash ring style orientation of distribution of raw data across the elements of the cluster. Then, and at a completely different layer above this, we have our model, which is built, our graph, and we have a web agent address space in which web agents are intercommunicating with other web agents simply via the URIs. Now, Swim has a ton of rich features which allows web agents to move between physical instances at runtime to meet computational needs for memory or CPU or bandwidth or whatever, or additional resources like GPUs. And also to deal with instance failover and other issues like outages. Okay, so the key thing I want to ensure that you understand is that at the layer of the application, the developer simply had to describe very simple things like, hey, I'm in section, I link to my neighbors, and I link and I learn. That's it. Okay, that's what writing an application in Swim is all about. You describe very simple things, and then at massive scale with massive amounts of data on arbitrary numbers of instances, all the stuff is hidden from you, the app developer. Swim just builds this big distributed mesh, okay? Peer-to-peer mesh, which can straddle clouds and so on. And I'm going to give you an example of that in just a sec. Okay, so a Swim application running at scale actually is as follows. So let's just say the traffic application that I showed you a moment ago running in the city of Las Vegas, it's 60 terabytes per day of data. Okay, what results from that is about 300 independent concurrent DNNs, each of which is learning and predicting from its own data and pushing up its own streamed predictions to an API in Azure. And that API in Azure is subscribed to by business interests, Uber, Lyft, and Google, and so on. Now we can push directly into something like a Kafka used by another consumer, or we could have a hokey kind of REST style API, which when you query it, will give you the right answers. But the key thing that I want to point out here is that instead of having one monster DNN or one monster model for Las Vegas, I have 300 independent DNNs, each of which is predicting for its own environment. Okay, so that's a very different application model than we normally assume for these environments. Okay, where do the predictions normally go? Well, if they're not going to an API, they could be going to a UI, and there is a complete TypeScript implementation of Swim which runs just in your browser. And so we can deliver really powerful real-time UIs that directly subscribe to Swim digital twins, these web agents, and deliver real-time experiences. Now, I've just given you a quick view of something which is called traffic.swim.ai, which is the traffic app for the city of Palo Alto. If you go and click on the little doobies, the blue intersections, or the colored elements, which are the phases of the lights, they'll tell you what they're doing. But for example, every one of those blue dots is an independent web agent, which is predicting its future. And you'll see the current and predicted future phase of the lights. Okay, so what do you mean by real time? I mentioned earlier that we're working with our biggest provider. Whoa, how do I get beyond this? Hang on one sec. Okay, cool. So I'm going to give you an example of huge scale in 1 sec. Let me just summarize where I'm at. So I'd like you to think of SwimOS as an extension for the Graal VM. You can write Java if you'd like. It's user mode, typically on Linux. Integrates superbly into the DevOps workflow directly as a result, using standard tools. I would point you to developer.swim.ai if you have any queries. Go play and ask them there. So what you'll find is all the tools necessary to build a fabric of SwimOS instances, to deploy an app, and to go to scale. When I talk about scale, I talk about billions, that's B, of digital twins, these little in-memory objects. Instances are deployed typically using Kubernetes, and we support hybrid and multi-cloud deployments. Okay, the rest you've got, and you can just go and play with. Okay, so here is an example of very large deployment using Swim. About 150 million devices build digital twins from real-time data delivered at a rate of about 10 gigabits per second. And the objective here is prediction of connection quality for mobile devices, and the objective is to optimize the connection quality delivered to every user. Okay, and so we can deliver this to a real-time user interface, or directly to other components, applications in the infrastructure, which can have an effect on user experience. I wanted to give you an opportunity to play with Swim literally right now. And to do this, I need to do escape, pull up my browser, and I'm going to ask everybody online who isn't doing something else to go to splash.swim.ai. in their browser right now. And then just touch the thing. Who's there with me? Anybody there? Oh, I see you. Cool. Okay. We're all in different places. Now draw shapes. Okay, you're gonna see. Okay. So splash.swim.ai isn't using a TypeScript in browser implementation of Swim, in which we are building these little digital twins, these little Java, these web objects for every finger touch on a screen. We're building those in real time on the client, and then the server is doing some analytics on the back end. Okay. And we're linking them together based on proximity and various other aspects. Okay, and you can go and dig into the cloud, but you can see that even though we're all a long way from each other, we're actually getting real-time responses in the browser. Okay, now I mentioned a large deployment of Swim on mobile devices. I want to point out the new mode, which is essentially NATS and Swim. Instead of about 400 nodes of Hadoop fronted by 300 nodes of Pulsar, 100 nodes of Pulsar, we end up with just a straightforward subscription, and we can do that by NATS. I don't know the server count there, but I do know that we only need 10 nodes of Swim. Okay, so the infrastructure cost for this style of processing is vastly lower. Okay, so I'm going to stop there because I know you're pressed for time, and I'm going to invite you to ask any questions.
Simon, thank you so much. As you know, I'm fascinated by the Swim AI platform and, you know, intelligent, semi-autonomous edge platforms in general, because I think they're kind of the future of compute, right? You know, one of the areas that you guys highlight in a lot of your talks is the ability to generate data, transport it to a cloud, process it, and bring it back is simply not going to work, right? As we keep moving forward. And where NATS, I think, can play a role, and we have 4 to 5 conversations every week with companies that are doing the same thing, is how do we enable these platforms? And I always say, I think you start with a trusted, secure, extensible, you know, messaging system that avoids things like tromboning. So the same thing of sending the data back to the cloud and coming back. If you're sending a message all the way back to the cloud and waiting for it to come back when you're trying to talk very quickly, let's say on, you know, a traffic light or a plant or a factory or a bicycle or a Bose headset or whatever that is, we keep seeing the same general need to solve these types of problems with what I consider, you know, semi-autonomous, you know, intelligent ed platforms. And I really think it's kind of the future of where not only things like, you know, infrastructure in cities like with traffic and smart cities and stuff, but again, just regular old, like coordinating between lots of plant factories, let's say for a car manufacturer, auto manufacturer, the problem looks very, very similar. And so thank you for the time. Thank you for being the home run hitter at the end, so to speak. But yeah, this is obviously really, really fascinating to us, and we love being able to play a small part in it.
Thank you so much for the opportunity.
Absolutely.